polynomial models. We have done some of this before. And then by the end of today, you're going to be able to use the finite differences to determine the degree of a polynomial that will fit a given set of data. We will also use technology, that's our graphing calculator, to find a polynomial for a given set of real-world data. So we've done linear models before, we've done quadratic. Now we are going to do a few more types. Okay, so we're used to finding the finite differences for the quadratic. Remember we did that on our chapter 2 test. Remember we had to write down when was it quadratic? What differences were constant? If it's quadratic, what differences are constant? The second. You guys remember what else we wrote down with that? The second difference had to be constant and non-zero, and the x values were evenly spaced. Okay, so if it's linear, it's going to be the first finite differences are constant. Okay, if it is quadratic, it's going to be 2. And then we also have the cubic, the quartic, and the quintic. Okay, so if the third differences are the same, it is cubic. If the fourth are the same, it's quadratic. So just do that. And then the fourth differences would be quartic, and then the fifth are quintic. So I also put just what type of model you would have there. So if it's a linear, your equation would have x is your highest exponent value, and then you have the x squared for quadratic, x cubed for cubic, x to the fourth for quartic, and x to the fifth for quintic. So what we're going to do today is, given a set of values, we are going to use the finite differences to determine if it is linear, quadratic, cubic, quartic, or quintic. Okay, so we're using those finite differences to determine what the degree of the polynomial is. Alright, so example 1, we're going to do some highlighting with that. And then I can put that back up if you guys are missing some of it. Alright, so example 1, use finite differences to determine the degree of the polynomial that best describes the data. Okay, so the degree, that means you're just going to name it. Okay, so name the type of polynomial. That's why we went over that chart, because we're going to actually name the polynomial. Alright, so you'll be given a table of data. In the past, we've done it where it is horizontal. This one is vertical. So your x values are 4, 6, 8, 10, 12, 14. Your y values are negative 2, 4.3, 8.3, 10.5. I think she'll be gone all week. And then 11.4, 11.5. So remember when we were writing this out before, the one thing we also had to check besides the differences is making sure our x values were what? Yeah. Okay, so make sure that you check for that. I just put x values evenly spaced, and I just put a little check saying, yep, they are. So those are spaced by 2's. Okay, and now we're going to find our finite differences. So we're going to find the first differences. And there's a couple different ways you can do this. You can either ask yourself, what do you add to -2 to get to 4.3, which is what? What would you add to -2 to get to 4.3? 6.3. Yep, you could do it like that. This one, that would be pretty simple to do as well. 4. Okay, for here, and really for anywhere, to find the differences, you can always take that second value and subtract. So 10.5 minus 8.3. Okay, and then you could also find it that way. Just be careful when you're doing that with a negative, because if you did 4.3 minus 2, that would not be the same as minus -2, which is what you have. Okay, so just be careful about that. Okay, and then 11.4 minus 10.5 is going to be, we'll find those last two. Did you guys already find them or not? Okay, Abby, what'd you get for this one? Good. All right, and then Danny, what'd you get for that one? 10.1. Yes. All right, so what you do is you say, oh, are those constant? Are they the same? Are these the same? No. So then we move on to the second differences. So we would find the difference between these two. And again, you can just do the 4 minus 6.3, or you can ask yourself, what would you add or subtract from 6.3 to get to 4? This one should be negative because you're going down. So this is negative 2.3. Okay, so practice doing this with me. The 2.2 minus 4, negative 1.8, 0.9 minus 2.2, negative 1.3, and then just verify. Yep, it's going down. Yep, it's going down. That one's 0.8. Okay, so they're still not the same, so that means I have to go to the third differences. Sometimes I write those first. Okay, and then it's negative 2.3 to negative 1.8. You're actually going up here, so it should be positive. So this is negative 1.8. If you guys want to skip the minus and negative and just put plus 2.3 because you know that's what's going to happen, that's fine. Instead of doing like the minus and negative in your calculator. Do you guys have a preference on how you do that? Do you like doing the plus in your head or what? What do you guys like? Or do you like doing minus and negative? You like doing minus and negative? Alright, and then 0.5 and 0.5. Alright, so yay! All of these are the same. Okay, that's what we call constant. So the degree is 3, and that makes this a cubic polynomial. Okay, so I do want you to say that it's a cubic polynomial. Alright, I'm going to let you try part B on your own. So negative 6, negative 3, 0, 3, 6, 9, and then your y's are negative 9, 16, 26, 41, 78, and 151. Alright, so I want you to find the constant differences there. And again, the first thing you want to check is what? What do you want to make sure you have? Yeah, the evenly spaced x's, which we do. All the x's are going up by what value? Yeah. first differences. So your first differences are 25, 10, 15, 37, 73. How do we do? Double check this first one, right? Because it's from -9 to 16. You're going up by 25. This is the one where I said you got to watch it on your calculator, right? So it's 16 minus a negative. Did some of you get 7 by accident? That means that you just did 16 minus 9 instead of minus the -9. And then our second differences, let's look at those. So you should have -15 because you're going down 15, right? Then from 10 to 15, you're going up 5. 15 to 37, you're going up 22. And then 37 to 73, you're going up by 36. Okay, so the signs matter. The positives and the negatives, those are going to matter. All right, then we got to the third differences. And to go from -15 to 5, we went up 20. 5 to 22 was up 17. 22 to 36 was up 14. And we still didn't have the same. So then we went to the fourth differences. And yay, they were both -3. So because those were the same, the degree is 4. And it is a quartic function. Okay, and it is a quartic function. Okay, what questions do you have for me on the first step? Okay, so this first example, this was in the nice math textbook world, which the math textbook world is lovely. We have these nice constants here, and that's great. But when we are working with data in the real world, we aren't always going to have constants, so we're going to talk about that. Yes?
So for the first one, you said it was a cubic polynomial. How is that, how do we know if it's a polynomial?
Oh, they all represent the degrees of the polynomial. So whatever difference you have, okay, whatever the constant differences are, that's going to tell you the type of the polynomial. So in this case, it was the fourth that was constant. So if it's the fourth that's constant, the degree is 4, and then that will be a quartic. And then for this one, the third one was 3, so then it's going to be a cubic. So remember when we did this earlier with the quadratics, we only found the second differences, and then we determined if it was quadratic or not? That's the same process here. Except we were only working with quadratics, so we didn't have to worry about the other ones. Sam, did I answer your question too?
Yeah, I was just wondering how you find it.
Okay. Yes. Thanks for sounding like that. Okay. So now what we're going to talk about is polynomial regression, and we've actually done the regression before. We've done quadrag and we've done linreg. Do those ring a bell? Is something that we've done before? Linreg was in chapter 1. So the types of regression, we have linear regression, okay, and we did that in chapter 1. We've done quadratic regression. That's in chapter 2, okay, and then now we're adding these to the mix. We're adding cubic regression, and we are adding quartic regression. So we've actually done these two before. We're adding a couple more to the mix, okay? So when we did the regression, we used our graphing calculator. Well, actually with linear, I showed you how to do it by hand and using a graphing calculator. So you can see that we're working with data. Do you guys remember how to enter or where the data goes when you're entering it in your graphing calculator? Do you remember where it goes? Okay, maybe we need a little reminder. So we're going to enter data into, and then do you remember what your variables correspond to? List 1 and list 2? Do you guys remember where those are? Yeah, you go to stat, and then when you want to edit them, you just press enter. You go to stat and then enter. And guess what? We will be doing that. Okay, so we are going to be using that function on our graphing calculator. And we're going to use that to help us find the polynomials. So let's explore how we can use that regression. Do you guys remember where quadreg is? You go to stat. That's the first step. And then where do you go? No. That would be to list, yeah, to enter in the list, which we'll do in a minute. But then where do we look at the regressions? Yeah, you arrow over to calc. So go to stat, arrow over to calc. Okay, and now you are going to be able to choose your regression function. Okay, so here we have the linreg. That's an option. And linreg usually does say the ax plus b behind it. You have quadreg. And then look, you have cubic reg. And you have quart reg. We're going to be using all the regressions. Okay, so when we start to talk about real-world data, when you're looking for these finite differences, this just says data. We're going to talk about real-world data, okay? You are not necessarily looking for a constant difference, okay? They're not going to be exact. So instead, you're looking for values that are close to each other. And sometimes that might not be easy to do, so we're going to talk about some strategies. So this is because your set of data is not going to fit a curve exactly. Okay? We don't necessarily live in a math textbook world where everything's nice and even and beautiful. Okay? We have to gather the data, and then sometimes we have numbers that are close but not exact. Okay, so this is more of an estimate. And then what we're going to use is something that we've used before called the correlation coefficient. You guys remember that buddy of ours? The correlation coefficient. I actually talked to somebody today who had to find the correlation coefficient by hand. Like that, and it made them cry. Don't worry, we're going to use the calculator. We're going to use the function on the calculator. Do you guys remember what the correlation coefficient is? What variable? R. Yes, good. And then the closer this number is to what, the better the fit. Yes. Okay, so the closer the number is to 1, or really, like in cases like where it's down, it could be -1 with linear. Okay, the better that the fit is. So the correlation coefficient is R squared. So before we were doing R, now you are going to see the R squared with the higher polynomials. Okay, and then I'll remind you how to get this on your calculator. Okay, so to get R squared, you have to turn your diagnostic on. Oops, I forgot my N. Diagnostic on. You guys remember how to do that? We'll do that together. You have to do this or you're not going to get your R value. And the main thing we're working with today are the R values. Okay, so you got to turn your diagnostic on. So we're going to go to second, and then you want to go to your catalog. Do you guys know where the catalog button is? Yeah, good. Yes, you're going to hit the second button. And then you go to your catalog, which is above the 0 button. Okay, so do that part with me. So second, 0. Okay, and here's your catalog of all these functions, but see how it starts at A? So if you want, you can scroll all the way down, or you know that we want diagnostic, so see the little letters on here? Find what letter? D, which is right here. It says matrix next to it. This is x to the -1 power, which means inverse. So you can hit that button. Okay, so I'm just going to put, once you do that, you go to the letter D. I'll put it in green since it's green on your calculator. All right, and then you are going to select diagnostic on, and it's all written together like that. Okay, so let's scroll down. There it is. Make sure you click the on and not the off, okay? There's been some cases. This isn't working for me. It's because you keep turning it off. Okay, so we gotta press enter, and then we gotta press enter again. Okay, so you hit enter twice, and then you will see it'll say done once you've done it. Okay, so give me the thumbs up when you have the done, the diagnostic done. Here, copy. Can you turn it on? Oh, okay. We'll trade so you can do this, okay? All right, so let's look at example 2. I want you to read through the directions, and then can you guys highlight what the direction is? Can you do that more people? Or you can underline, what it's asking you to do. So what is the direction they're telling us to do? Yeah, we have to write a polynomial function, okay, that is going to fit this data. And then there's another thing that they tell you to do. Make sure that you label what your x and your y represent. We're going to talk about that. Okay, so we want to make sure we label what the x and y variables represent. Okay, so when you are entering in your data, and it's in terms of years, okay, this is your input, this is your x. But instead of putting in 1960, which is going to give you like some large numbers to work with, do you guys know how we could label the x and what we could put in for this year here? That you could, or you could just make this your starting point. Your starting point, your initial value, that could be 0, right? And if that's your 0, what would 1970 be? 10. Right? And then the 1980 would be 20. 1990, 30, 2000, 40. Okay? Now, what we are going to label our x, once we write out our equation, is this is the number of years since 1960. Okay, and then we have our y value, which is going to be the population, and then notice it says in thousands, so they've actually done the y for us. Just know that this is in thousands, which means this number represents the 4267 times 1,000. So you would have 3 more zeros at the end, okay? Which makes sense. It's talking about the population of a city here. I guess these could be like really small cities. There are small cities, but then this would be if you did the zeros on there, 4.2 million. Okay, so those are some larger cities there. Okay, so let's go ahead and let's find our finite differences. Okay, so the first thing we're going to do is find the first differences. So we have this one to find, this one to find, this one to find, and this one to find. So just like we were doing before, we are going to take the 5185 minus 4267. Okay, we get 918. Okay, and then we're going to keep doing this. For sake of time, I am going to give you what the differences are for this first one. Okay, and again, you're just subtracting just like I showed you there. Okay, now these two seem pretty close together, but then as I get down here, right, this is almost half of this number. So I'm going to go ahead and I'm going to find my second differences and see if those are a little bit closer together. So for my second differences, okay, 981 minus 918 is going to give me 63. Subtract here to get 683. Subtract here to get 1318. Okay, so again, these seem kind of far apart, right? This is over 600 apart here. This is more than 600 apart here. So let's look at our third differences. And then this is 620. This is 635. So yay, those are very close. Okay, so if the third differences are close, that means when I go to my calculator, I am going to want to use the cubic regression. So these are close differences. Remember with the data, it's not going to be exact. And because it's the third difference, I'm going to use my cubic regression. Okay, so in order to use cubic regression, we have to plug in list 1 and list 2. So let's go ahead and do that part together. So we're going to go to Stat, and then Enter. Oh yeah, my list 1 already says it. I'm just going to clear it out. So you're going to have 0, Enter, then 10, 20, 30, 40. Okay, and then if you need to clear this out, you can press Clear Enter. And the first one is 4267, 5185, 6166, 7830, and then 10,812. Okay, and then just look up at me when you have those entered so I know you're ready for the next. I appreciate your intentional looks. All right, so now we're gonna go to our Stat, arrow over to Calc, and then remember what we said. We're gonna do cubic reg, and we're gonna look at a couple things here. Once I press Enter. This is the screen where some of our calculators are different. So some of us are going to have this screen. You can just arrow down to calculate. And then you should end up with this. Okay, so one thing I want you to notice is the R squared value. We're going to write that down. Are you having trouble getting there? Okay, give me a second and I'll come back and help you, okay? And then, so your R squared value, we're going to round this out to the nearest thousandth, so 3 places after the decimal, okay? I can see my R value is 0.999. So would we say that this is a strong correlation or a weak correlation? Very strong, yes. Yes. And then for the cubic regression, they told you that it's y equals ax cubed plus bx squared plus cx plus d. Alright, so do you guys think you can round those to the nearest thousandth and write your polynomial out there? So 3 places after the decimal, that's what you're going to round to. then once you've done that, I want you to go and do the same thing with quad reg. And we're going to look at the R value for that. Oh, you go to that. And then enter. But make sure that you enter the 010, not the 1960, okay? And make sure that you guys did enter in the 0, 10, 20, 30, 40. Mm-hmm.
Why is it, was it even considered?
We're going to go for that. Okay, so let's go ahead and make sure that you guys rounded this correctly. So your polynomial should be y equals, and yeah, these polynomials mean business here. Right, they're lengthy. So this one is 0.105 x cubed because you had to round up. And then this would be minus 2.83, and then it would round up to 9x squared. The next one is positive, so this is going to be plus 109.835 when you round. And then you have the x with that. And then the last number is the 4,266.786 when you round. Okay? And then this is where we just have to say what our variables are. So this is where x is the number of years since 1960, and that's why 1960 starts with 0. Okay, so it's in 1960, it's 0 years since 1960. And y, and they actually told you what y is the population. So you could say the city population. In thousands. Okay, so I asked you to use the same data and do the quad reg because I want to show you something. We're going to do this several times. So if I were to do the quadratic regression for this guy, okay, my R squared value, again, I'm going to round it to 3 decimal places and look and see why. Right? My R squared value for the quad reg is about 0.994. Right? So which one's stronger? Well, obviously the cubic, right? Because it's 0.999. And then you could do the same thing with linear. So go over to calc. Okay, and then for the lin reg, your R squared is going to be 0.965. Okay, so if you found those, it would obviously be that your cubic regression here would be the strongest. But there's one more we can find. What else could we find? Yeah, let's do the quart reg. Let's find that. Okay, so will you guys find that for me? What? Yeah, what? So, what's the R value for the quart reg? I did quad. It's like, what? Okay, the R squared value is 1. That's interesting. So really, we should think that that one would be the strongest, right? If it's equal to 1. But let's look at our values here. You see any values that look a little different? A. A is 6.25 e to the negative fifth. What does that mean? Yeah. Yeah, because you guys are doing your sig figs right now, aren't you? Yes. Okay, so 10 to the negative fifth. So if I were to do this, it would be 1, 2, 3, 4, 5. So it would be 0, 0, 0, 0. So that rounds to what? 0. Wouldn't A be approximately 0 in this case? Yeah. So guess what? If A is approximately 0, if you had 0, x to the fourth as your rounded value, would that be a quartic? No. It would be a cubic. Okay, because you wouldn't have any x to the fourth value. Okay, so because your A value is approximately 0, so r squared equals 1, but A is about 0, which makes, or we can say which means cubic is the best fit. Alright, and then this is what we're going to use in example 3. Okay? So I want you to take a look at example 3, and I want you to see what we can label those. Okay, what can we label those? Oh, that woke me up. Okay, so when you think about the years, think about where you're going to start.